What if everything around you now is not real, and they only exist because you are there to observe it? It may sound like a philosophical question, but it is one that has puzzled humans for centuries. Now, what exactly do you mean by reality? Would you say it's the physical world we see and interact with, or is it something more abstract, such as our thoughts and emotions? Or let's define it like this. It is the totality of all things, structures, events, and phenomena that exist, whether observable or not. But this definition acknowledges that reality extends beyond the physical world that we can see and touch, and includes abstract concepts, such as thoughts, emotions, and ideas. You see how difficult it is to understand its true nature. Have you ever experienced that you've awoken from a dream, only to find out you are actually still sleeping? Dreams within dreams happen sometimes. René Descartes, one French philosopher, argued that if we cannot even tell for sure whether we are dreaming, then how can we know for certain any truth about the world in which we seem to live? His famous statement, "I think, therefore I am," comes from the realization that to think, one has to exist, and that is the only truth beyond any doubt. Chinese philosopher Chuang Tzu dreamt about being a butterfly, fluttering hither and thither, to all intents. According to Chuang, he was conscious only of his happiness as a butterfly, unaware that he was still a human being. When he finally woke up, he said, "Now I do not know whether I was then a man dreaming I was a butterfly, or whether I am now a butterfly, dreaming I am a man." Between a man and a butterfly, there is necessarily a distinction. Another great philosopher, Plato, explored these questions in his famous allegory of the cave. The allegory of the cave begins with a scene painted of a group of prisoners, who have lived chained to the wall of a dark cave their entire lives. Behind them is a walkway and a fire being set to display shadows on the wall in front of the prisoners. Every day, these people in the caves watched shadows projected on a blank wall. For them, these shadows are real and they shape their entire reality. Now, imagine that one of the prisoners leaves the cave and walks outside into the sunshine. For the first time in his life, he is exposed to sunshine and light. He can now finally see the true forms, shapes, and reality of the shadows he thought were real. In this allegory, what would he think of his companions back in the cave? He'd probably feel sorry for them and their limited reality. Now, if he returned back to the cave and told them about what he saw, they'd probably laugh at him and think he was crazy. Plato's allegory of the cave explores the tension between the imagined reality that we think is real, which we might refer to as shadows in this situation, versus the reality that is the truth, a reality outside the cave instead of shadows. Plato's allegory of the cave illustrates at least two things. First, it represents Plato's account of the nature of reality and his understanding of essence. Second, it's a lesson in what philosophy does, it reveals the true nature of things. Without doing philosophy, we remain in the dark. To sum up, Plato's cave is an allegory of the human condition. Each of us is a prisoner, chained down with a distorted illusion of reality. To gain individual autonomy, one must awaken our consciousness, we must kill our imperfections, and liberate one's senses. If the school district system were to say tomorrow that 2 + 2 = 5, and no longer 4, many will follow the new rule because they are mathematicians and they know more than we don't. Hence, what they say is true. All these people play a role in creating this false reality or shadow reality that we all perceive as true reality. We don't have individual autonomy despite the system stating that we possess such fundamental freedom. So what do we have to do? Your reality is a perception, or as the Hindus like to call it, the Maya. Your 5 senses only allow you to perceive a mere figment of reality. The 3-dimensional nature of our world limits our worldview with its duality paradigm, prevailing in all aspects of our experiences on Earth. Think about it, there are no absolute truths in this world, there are only different lenses of perception. The stars you see in the sky are in reality glimpses of your past. The colors you perceive as red, yellow, blue, and so on, are only reflections of different wavelengths of light. The average human body contains around 7 octillion atoms, and they all seemingly know exactly what to do in order to successfully perform their function. Hidden webs of information must, therefore, be guiding the atoms and molecules in their biochemical reactions, while at the same time obeying the laws of quantum physics. All this occurs within the subsystems of the cellular machinery. Consciousness might be universal, in the sense that every system might have some degree of consciousness. This view is sometimes called panpsychism. Every system is conscious, not just humans, dogs, or other animals, but even microbes. Even a photon can have some degree of consciousness. The idea is not that photons are intelligent or thinking, but maybe photons might have some element of raw, subjective feeling, some primitive precursor to consciousness. This may sound a bit kooky to you. I mean, why would anyone think such a crazy thing? The motivation comes from the idea that perhaps the most simple and powerful way to find fundamental laws connecting consciousness to physical processing is to link consciousness to information. Wherever there's information processing, there's consciousness. Where there is complex information processing, like in a human, there's complex consciousness. And where there is simple information processing, there's simple consciousness. Long before quantum physics had been developed, in the early 19th century, Arthur Schopenhauer developed his philosophy of will, which he published in a ponderous tome called The World as Will and Representation. Schopenhauer's main thesis is that the world can be divided into two pieces, will and representation. Simple enough. But for him, these had very specific meanings. Representation is how the world appears to us. That could be either the color of a flower or the spin of an electron. Will is the underlying essence of things. Schopenhauer's ideas suggest that the underlying reality of the universe is not one of essential determinism but of will. And that would determine how reality is represented to us, even objective measurements like the position or momentum of a quantum particle. One interpretation of quantum physics is that this is exactly true. In quantum physics, we have the mysterious phenomenon of entanglement. In entanglement, two particles are correlated with one another, such that when you measure one it affects the other. At the most fundamental level of our existence, reality is far from being objective. Rather, it is analogous to a series of interwoven subjective experiences fed into your awareness. Experiments like the double-slit experiment and Schrödinger's cat thought experiment challenges the traditional notions of what makes up reality. The laws of quantum physics are different from the laws of the physical universe. To understand how consciousness creates reality, you have to know how particles behave at the most fundamental level of our being. Some of you may ask this question: what do physicists worship? A single theory or equation that can describe every single behavior and movement of large stellar galaxies to small and strange quantum substances, a single theory that can unify all the physical laws in our universe, a theory of everything. Over the last century, we've ripped atoms apart, eventually finding electrons and quarks, the fundamental building blocks of stuff. But are they really fundamental? Have we truly reached the bottom? Physicists like to reduce the description of the mechanics of our reality down to the simplest possible form. They expect this simplest form to have minimal parameters or moving parts. This is where the idea of string theory comes from. Some physicists believe that reality is made up of infinitesimal vibrating strings, smaller than atoms or electrons. The vibrational state of these strings is what determines the properties of the elementary particles that we observe. For example, a string vibrating at a certain frequency with a certain amount of energy gives rise to a particle called an electron. And they vibrate at countless billions of times per second in 10 dimensions of space. But why would physicists think this is the way the universe operates? To understand why, we need to step back more than 100 years. At the end of the 1800s, scientists thought they understood gravity, electricity, magnetism, heat, and gases. In 1900, Lord Kelvin apparently retorted that there is nothing new to be discovered in physics. But soon after the dawn of the 20th century, this situation began to fall apart. Einstein rewrote the very notions of space and time with his special and general theories of relativity, whilst Planck, Bohr, and Heisenberg revealed that the world of the very small obeyed the apparently nonsensical rules of quantum mechanics. By the mid-1900s, our view of the universe had been utterly revolutionized. And these new strange physical theories were yielding incredibly accurate predictions for experimental tests. The idea of string theory started in the 1960s, when physicists were trying to understand hadrons, which are composite subatomic particles made of two or more quarks held together by the strong nuclear force, similar to how molecules are held together by electromagnetic force. Hadrons include protons, neutrons, and mesons, which are composed of a quark and an antiquark. Quarks are subatomic particles that are believed to be indivisible and have no substructure. They are not static entities with a fixed position, but exist as a wave of probabilities and only manifest in a specific location when observed. During the study of the interaction between pairs of mesons, physicists noticed peculiarities in their relationship between angular momenta and masses, leading them to suggest that the quarks inside the mesons are connected by strings. These strings can be described as elastic bands made of gluons, a type of elementary particle responsible for the exchange of the strong nuclear force between quarks as they vibrate. Physicists began developing a quantum theory to explain the strong nuclear force, but this was soon replaced by quantum chromodynamics, since the string theory of the strong nuclear force described an unexpected vibrational mode that was unwanted. This unexpected mode described a hypothetical particle known as the graviton, which is the quanta of the gravitational field. However, physicists realized that there was no reason for the graviton to appear in the investigation of hadronic string, and therefore abandoned this theory. Physicists discovered in the 1970s that the mathematics of string theory could describe quantum gravity, the final piece needed to complete the theory of everything. After extensive mathematical calculations and adjustments to the hadronic string theory, scientists were able to unify all the physical laws in our universe on paper, but to do so, they had to add 22 extra dimensions on top of our 3 spatial and 1 time dimensions. This theory became known as the bosonic string theory, which was able to explain force-carrying bosons. Encouraged by this success, physicists proposed the idea of supersymmetry to bring fermions and bosons into the same theoretical framework. The principles of supersymmetry and string theory were combined to form superstring theory, which states that every boson has a fermion superpartner, and vice versa. This theory reduced the total number of dimensions required to explain the underlying nature of our reality from 26 to 10. This was the first superstring revolution, which presented 5 theories where one-dimensional quantum strings moved around in 10 dimensions of space-time. Sometimes different mathematical theories describe the same physics. This is called duality. Superstring theory is awash with dualities. There are 5 different versions of superstring theory, each representing a different type of superstring. In 1995, physicist Ed Witten developed a way to unify the many forms of superstring theory into a single framework called M-theory, which requires an additional dimension, bringing the total to 11 dimensions. Although there is no string theory in 11 dimensions, there is a supersymmetric theory of gravity known as supergravity. Supergravity includes a theory of supermembranes, which are surfaces called membranes that must be included in M-theory for it to work in 11 dimensions. According to supergravity, the one-dimensional quantum strings can stretch across different dimensions, forming membranes. These membranes exist within a hyperspace that contains universes attached to them, and together they form the multiverse. Our universe is located on one of these brands. It should be noted that M-theory is an attempt to unify the theory of general relativity, supersymmetry, and string theory. Witten explained M-theory to be the skeleton, while the 5 superstring theories to be individual bones. Our understanding of M-theory is by no means complete. Even after identifying dualities in the strings and hints of supergravity, the middle of the web remains impenetrable. Even with our current knowledge of this theory, we can predict or explain multiple phenomena that could not be explained using our best theories in physics. String theory explains why gravity is weaker than the other 3 fundamental forces. It shows that gravity permeates through different brain universes. It seeps through our brain universe into other brain universes and higher dimensions. The second thing it attempts to explain is how our universe came to be. Our best theories break down at the moment of the Big Bang. String theory gives us its own unique explanation of how universes are born. Universes are born out of brain collisions or brain separations. This is the promise of string theory. At present, the most certain experimental procedure for string theory lies at the point that is inaccessible with our current technologies. In the meantime, string theory continues to offer delightful insights to our impossible problems. Maybe the story of string theory might not be the theory of everything, but it is a useful one. As wrong or incomplete our current string theory may be, It may also be the inevitable step to point us in the right direction of understanding reality. In ancient India, there was a philosopher named Shankara who told the story about an elephant and a group of blind men. A group of blind men heard that a strange animal, called an elephant, had been brought to the town, but none of them were aware of its shape and form. Out of curiosity, they said, "We must inspect and know it by touch, of which we are capable." So, they sought it out, and when they found it they groped about it. The first person, whose hand landed on the trunk, said, "This being is like a thick snake." For another one whose hand reached its ear, it seemed like a kind of fan. As for another person, whose hand was upon its leg, said, "The elephant is a pillar like a tree trunk." The blind man who placed his hand upon its side, said that the elephant is a wall. Another who felt its tail, described it as a rope. The last felt its tusk, stating the elephant is that which is hard, smooth and like a spear. The parable has been used to illustrate a range of truths and fallacies. Broadly, the parable implies that one subjective experience can be true, but that such experience is inherently limited by its failure to account for other truths or a totality of truth. Shankara used this story to illustrate the idea that reality is not always what it seems. We may all be looking at the same thing, but our perceptions and experiences are unique to us. This means that our understanding of reality can be limited by our own perspectives and biases. According to Shankara, the only way to truly understand reality is to look beyond our own limited experiences and try to see the bigger picture. By doing so, we can gain a greater understanding of the world around us and find the truth that lies beyond our own subjective experiences. Have you ever seen The Matrix? Chances are that you have. It's a rather popular film. One of the most memorable moments in the film is when Neo is presented with the choice between the red pill and the blue pill. If he chooses the red pill, he will learn the truth about reality, no matter how difficult or painful it may be. If he chooses the blue pill, he will remain blissfully ignorant of the true nature of his existence. Neo chooses the red pill and learns that he has been living in a simulation all along. However, the concept of true reality is called into question when we consider that the red pill doesn't simply grant knowledge of reality, but rather blurs the lines between what is real and what is not. This begs the question, is Neo's present experience after taking the red pill actually real? Or could he still be inside a simulation, within another layer of reality? As we delve deeper into this idea, it becomes apparent that knowing what reality truly is, may be an impossibility. The Matrix only serves to prove that we may never be able to distinguish what is real and what is not. It's conceivable that we could be caught in an infinite cycle of simulations within simulations, each layer more complex than the last, without ever reaching any true reality. Just a simulation within a simulation within a simulation within a simulation. The idea that our universe may be nothing more than a computer-generated simulation has been a topic of philosophical debate for centuries. With the increasing power and sophistication of computing technology, it's not hard to imagine a scenario in which we have enough computational resources to simulate every single particle in the universe over the course of its history. If computing power increased to great enough levels, we could, in principle, simulate every particle in the entire universe over the course of its history. If the computer we created was a quantum computer, capable of keeping every single particle in an indeterminate quantum state, it might be able to incorporate this fundamental quantum uncertainty everything seems to possess. Maybe the simulation we live in just began seconds ago and we only think it's been 13.9 billion years, because that information was artificially included upon its creation. Maybe the universe is much smaller than we think, and all the distant galaxies, stars, and planets that we see are nothing more than simplistic representations, created by the simulation to give the illusion of a vast and expansive universe. In this scenario, the simulation would only add detail and complexity when it's needed, rather than having it be a constant and absolute property of our reality. Or maybe nothing physically exists until we are there to observe its existence. And the craziest part of it all is, maybe discovering that this is all a simulation is part of the simulation. Nick Bostrom, a Swedish philosopher, proposed in 2003 in his paper, "Are You Living in a Simulation?" that in the future, a technologically advanced civilization may be capable of creating simulations of their ancestors. These simulated individuals would possess an artificial consciousness that distinguishes them from the AI robots typically depicted in films, as their consciousness originates from a real person who lived on Earth in the past. Today, nearly 2 decades later, this concept seems increasingly plausible, especially given the current pace of progress in the field of AI. This arises a very interesting question. Let's say that the key element of a simulation is that the characters do not realize that they are in one. How do we know that the consciousness that we possess, or that voice inside our head which speaks to us, belongs to us in the first place, and not some ancient race brought around in this world again by its advanced descendants? Considering humans are almost about to habilitate another planet, just 300,000 years after our first appearance on this planet and starting from literally nothing, it is fairly credible to say that given a few more years, the advanced descendants of our race would be capable of traveling through galaxies with ease, and even create their own simulated beings, which leads us back to the very beginning and hence validating the above theory. The sole purpose of chasing this possibility and understanding the purpose of our existence is to try and understand what kind of a game we are part of to improve our chance of thriving and surviving. While the nature of consciousness, the concepts put forth by string theory, and the possibility of our existence as simulated beings all provide interesting insights into this question, there is no definitive answer yet. As humans, we experience the world through our senses and interpret this information through our consciousness. However, it is still unclear whether our perception of reality is a true representation of what actually exists, or simply a construct of our minds. The implications of this question are far-reaching, as they challenge our fundamental understanding of ourselves and the universe around us. It prompts us to ask questions about the nature of existence, our purpose in life, and our place in the grand scheme of things. In the end, it is up to each individual to grapple with this question and come to their own conclusions. Whether we are living in a simulated reality, a multiverse, or the only reality that exists, one thing is certain. The pursuit of knowledge and understanding of the universe around us will continue to push the boundaries of what we consider to be reality. In one of my previous videos about this topic, I talked more about how important it is to understand that we're not seeing reality. Instead, we're seeing a story that's being created for us by our broken brains. You can watch it by clicking the video up on your screen. Thanks for watching, and subscribe for more videos.
This is Potbelly Hill. Situated in the arid hills of southeastern Turkey, the mound had long been considered sacred by the local Kurdish people. On a clear day, the view from the hill was breathtaking, providing just enough height to see all the way to the distant horizon, irrigated farms filling the surrounding flatlands. But by the mid-20th century, archaeologists had started to realize that Potbelly Hill was more than just a good vantage point. It was clearly the remains of an ancient village, abandoned long ago and covered in millennia of dirt. However, seeing nothing of exceptional importance except what was thought to be grave markers, they had moved on. And so it wasn't until 1994 that another archaeologist, the German Klaus Schmidt, heard of it from the locals. Guided by farmers to the location of the hill, he took it upon himself to set about his own excavation. He soon realized that these large underground stones were not grave markers, but the tops of huge megaliths. Further work revealed a tremendous complex, including towering, T-shaped pillars, long, arching paths, and concentric circles of imposing stone walls. But that was not the biggest surprise. For once archaeologists were able to date the structure, its age astounded them. The complex was over 10,000 years old. Potbelly Hill, which in Turkish translates as Göbekli Tepe, was discovered to be one of the oldest structures ever built by humans. Constructed right at the end of the last ice age and the transition from hunting and gathering to a more settled lifestyle, archaeologists still don't know the true purpose of the site. It may have been a fully functioning village or merely a sacred annual gathering place. Either way, Göbekli Tepe was vitally important to the people who built and used it. But after they abandoned it, again for as mysterious a reason as to why they constructed it in the first place, it was lost. Thousands of years of human history, hundreds of cultures and dozens of major civilizations waxed and waned through the area, never considering it more than an old hill with some rubbish buried beneath the surface. Göbekli Tepe serves as a major cornerstone for our modern understanding of the development of human civilization. Without it, our own past would be that much more mysterious, and it was built only 10,000 years ago. As we push deeper into the past, the story of our origins becomes even murkier. With fossil fragments scattered across the globe, we can piece together the general story of human evolution and development. Beyond that, we understand no more than the outlines. Indeed, scientists estimate that we have fossil evidence for less than 1% of all the species that have ever lived. And that is just life on Earth. We have only just begun to explore the wider cosmos with our probes and our telescopes. The vast majority of the universe remains completely unknown and unmapped. What mysteries await us there? How far back can we push the origins of not just ourselves and life on Earth, but life in the universe? Like Göbekli Tepe, what ancient monuments to life await us in the depths of interstellar space? Are we among the first generation, or the latest in a long line? Due to the Sun's larger space-time curvature, you would get about 67 seconds less per year on its surface than on Earth. Which is disappointing, as sometimes it feels like we don't have enough time even here. This video has been sponsored by BetterHelp, and they are the world's largest therapy service. Before BetterHelp, I personally didn't have a clue on how to access the right therapy for me. I just didn't have the time to sort it out, whether on Earth or on the Sun. But with BetterHelp, you can instantly tap into a network of over 30,000 licensed and experienced therapists who can help you with a wide range of issues. To get started, you just answer a few questions about your needs and preferences, and BetterHelp can match you with the right therapist from their network. You can schedule live sessions when it's convenient for you. With BetterHelp, you get the same professionalism and quality you expect from in-office therapy, but it's all much easier to sort out and at a more affordable price. So get 10% off your first month at betterhelp.com/HOTU, and I've also linked them below in the description. Thanks to BetterHelp for supporting educational content on YouTube. The lone dark rock stood out, a blemish on the otherwise perfectly smooth, perfectly white ice sheet. It had sat there for thousands, tens of thousands of years, undisturbed save for the rare snowfall. And Roberta Score could not ignore it. A lab manager from NASA's Johnson Space Center, Roberta had been there in Antarctica, spending the nightless hours scouring the vast ice fields of that frozen continent, hunting for rocks exactly like it. Antarctica is a surprisingly fertile ground for such finds. The rocks stand out clearly in contrast to the blinding white ice. Though at first Roberta's rock, found in the Allen Hills far western ice field and so named ALH 84001, seemed unremarkable, but in reality, it was anything but. For it turned out to not only be a meteorite, having fallen from space millennia before, but upon returning it to Johnson Space Center, the team discovered that it was no ordinary meteorite. It was a piece of Mars. Matching the chemical composition of the Martian surface, the rock must have been blasted off the red planet millions of years before during a titanic collision, then spending eons wandering the interplanetary depths before falling to Earth, where it had rested undisturbed ever since. The team sampled and studied this Martian exile, then made it available to the wider scientific community. And so it was nearly a decade later when another team, led by physicist David S. McKay, made a startling announcement. The unassuming meteorite contained microscopic features that could not be the work of mere chemical processes. Electron microscopy revealed chain-like structures that resembled living organisms found on Earth. This little rock contained the fossilized evidence of life on Mars. NASA announced the discovery to enormous fanfare, with even the then President of the United States, Bill Clinton, giving an official statement. But after the celebrations died down and other scientists got a chance to perform their own examinations, these further studies immediately cast the original announcement in doubt. Martian chemistry, they said, did not have to exactly follow Earth chemistry, and they could concoct a dozen different scenarios to generate chain-like features from nothing more than interesting combinations and reactions of chemicals. Fascinating, certainly, but not alive. ALH 84001 remains the only physical specimen to ever even offer a hope of identifying life outside the Earth. And the debates surrounding the nature of its microscopic structures serve as a potent lesson. Could we even identify alien life if it was staring right at us? To identify life, we must first define it, and the scientific literature currently contains over 200 different definitions. That said, a very general classification scheme is able to encompass almost all definitions. And that scheme relies on life having three distinct properties. 1. Life must be able to store information. Whatever the means, life must encode information about its current state. It must also store information about its own traits and characteristics and the information required to generate various processes. 2. Life must be able to catalyze reactions. It must be able to interact with the environment that surrounds it, responding to it and generating reactions of its own. These reactions allow life to acquire, store, and expend energy. They allow life to move, they allow life to react to signals or threats. And lastly, these reactions allow life to grow new structures. And 3, what separates life from non-life is the ability to self-replicate. Life must be able to make copies of itself, and these copies must be as faithful as possible to the original. Putting these 3 things together allows life to live. Famed physicist Erwin Schrödinger was the first to identify the fundamental principles of life from a physical point of view, correctly hypothesizing that the storing, utilization, and passing of information was of paramount importance. The information stored in life gives it the instructions it needs to catalyze reactions, and some of those reactions include the ability for life to replicate itself. Life can then go on and do all the things we normally associate with living. It can move, eat, protect itself, send and receive sensory signals, and most importantly, reproduce. This complete cycle also allows life to be subject to natural selection. Pressures from the environment work on the information passed from one generation to another, selecting some traits as beneficial for survival and disregarding others. And that in itself offers another definition of life. Life is that which is subject to Darwinian evolution. On present-day Earth, we can see a clear example of this definition. Us. We are quite literally living it. We have DNA to store information, we have our proteins that catalyze reactions, and we have RNA that acts as a translation tool from the information stored in our DNA to the production of proteins. And to complete the loop, our DNA can issue instructions via RNA to create proteins that go on to make copies of our DNA, passing on our genetic legacy from one generation to another. It's safe to assume that all life in the universe fulfills this basic definition. If it didn't, we would have a very hard time identifying it as living. To put it simply, to search for life, we must have a working definition, even if that definition isn't as broad as it potentially could be. But even on our own planet, and with that definition in hand, we run into interesting edge cases. A virus is alive, they store information and engage in reproduction, but they can't do it alone without a suitable host. And what about abiogenesis, the appearance of life on the early Earth? At some point, a collection of chemical processes went from non-living to living, and that boundary was probably blurry. The modern triad of DNA, RNA, proteins couldn't have possibly existed in the first life, because if you take one of those out, the cycle of life cannot complete. So early life had to be simpler. One hypothesis states that early life was solely composed of strands of RNA. These earliest forms of life would have been completely alien to what we have now in the modern world. Some aspects of early life we still find in common with our own. For example, early life still used liquid water as a solvent, and solvents are critically important for our understanding of life. This is because the life on Earth uses a soup of complex molecules to go about living, storing information, catalyzing reactions, and so on. These molecules need a place to hang out where they won't get instantly destroyed, and water is stable enough for exactly those purposes. Plus, water can bind with many other molecules, it can dissolve the ones you don't want, acting as a form of waste management, and it can be easily blocked, allowing you to build a membrane so that you always have just the right amount near you. In addition to liquid water, early life also experienced roughly the same temperatures that we do today. Even though the first life may have been extremophiles, like bacteria that can survive in deep-sea hydrothermal vents, that is still within the broad range of Earth normal. Early life didn't arise in the depths of interstellar space or on the surface of the Sun. Early life also used all the same elements that we're familiar with today. Carbon is exceptionally handy, as it can bind easily with itself and many other elements, allowing it to form large, strong structures. Oxygen is great for participating in chemical reactions, which means it can serve as a useful tool for storing and later using energy. Phosphorus, nitrogen, and hydrogen also play important roles, especially in the construction of DNA and RNA. So perhaps, early Earth life would not be so alien after all. The same solvent, the same temperatures, the same elemental building blocks. Those microscopic critters, however they initially emerged, would have the same basic requirements we do: water, food, and energy. But anything off the Earth is a completely different story. Perhaps what happened on our planet is generic, and almost all forms of life in the universe need the same basic ingredients: water, carbon, sunlight, etc. Or perhaps not. After all, we only have one data point to go on. And this was one of the major reasons why the Martian meteorite was so fascinating. Early Mars had liquid water on its surface and a temperate climate. But Mars also features chemical and geological processes that are unique to that planet, especially in the billions of years after its oceans evaporated. And so we must be exceptionally careful when studying other worlds. Thankfully, other places in the solar system give us the opportunity to test how broad our definitions of life can be while still being recognizable. Many of the outer moons in the solar system, like Enceladus and Europa, contain vast oceans of liquid water. But that liquid water is locked under miles and miles of ice, preventing any sunlight at all from reaching it. Not all life on Earth requires sunlight, so could life have gotten started there in the darkness of the oceans? Could a complex food web evolve, driven by organic material drifting through the icy crusts, fed upon by microscopic organisms, to be swept up by whale-like, eyeless giants? And then there's Titan, one of Saturn's 145 moons. The second largest moon in the solar system, it was discovered by the great astronomer Christian Huygens in 1655. That world is cloaked by a dense atmosphere rich with nitrogen, and it is the only known world other than Earth to support lakes and rivers on its surface. But at a temperature of minus 180 degrees Celsius, these aren't lakes and rivers of water, but of liquid hydrocarbons, like methane. Could methane serve as a solvent for an exotic, low-temperature form of life? perhaps even multicellular creatures relying on achingly slow metabolisms, could swim in those seas. Research continues, but the only way to find out for sure would be to go there. The immense atmospheres of the outer planets may also seem uninhabitable to us, but no one can be sure what strange physics and exotic chemistry play out in those depths. Heat, motion, complex compounds, all the ingredients are there, buried layer after layer in those atmospheres. Could creatures that never know the feel of the ground or the taste of water float majestically in those worlds? And lastly, there are all the forms of life that we can encompass in our imaginations. Perhaps somewhere in the universe, life uses silicon rather than carbon as a building block. Perhaps life doesn't even need chemicals to store information or make copies of itself. Strange quantum systems could do the trick, or forms of matter not known to us yet. But to begin our exploration of the earliest life that could possibly arise in the universe, we will start with the strictest definition of life that we can imagine. Life that looks like the kind on Earth, that uses water as a solvent in a range of habitable temperatures using a set of key, elemental building blocks. In 1952, a graduate student at the University of Chicago named Stanley Miller developed an experiment to test a controversial hypothesis developed by his advisor, Nobel Prize-winning chemist Harold Urey. The experiment was simple. Miller took a flask of water and added a mixture of methane, ammonia, and hydrogen. He then ran a spark of electricity through the flask. At first, nothing happened. But after a day, the mixture turned faintly pink, and after a week, the flask was filled with a deep red liquid. After adding additional chemicals to prevent microbial contamination and to stop the reaction, Miller used a chromatograph to identify what new molecules had appeared inside the flask. The results astounded him. Glycine, alpha-alanine, beta-alanine, aspartic acid, alpha and aminobutyric acid. These were amino acids, the building blocks of RNA and DNA, the basic chemistry of life itself. Miller's experiment shook the world. Prior to his work, philosophers, theologians, and scientists had only vague guesses of how life could have arisen on the early Earth. Now, the problem of abiogenesis was planted firmly in the scientific domain. Miller's experiment had shown how a mixture of simple, common molecules could produce the basis for the rich organic chemistry of life. The inputs into the experiment, water, methane, ammonia, and hydrogen, are all amongst the most common molecules in the universe, and are made of carbon, oxygen, hydrogen, and nitrogen. The outputs were amino acids, which are much more varied and complex arrangements of those same basic elements. Amino acids play a central, foundational role in biochemistry. Our DNA encodes information for 20 of them, and combinations of amino acids give rise to our protein structures, and all of life on Earth. The experiment had simulated the hypothesized conditions of the early Earth, a warm mixture of what are known as prebiotic molecules. The spark had simulated a lightning strike in a primordial pool, triggering a chemical transformation that would one day lead to life as we know it. While we still don't understand the path that led from the prebiotic early Earth to a world rich with living beings, the Miller-Urey experiment conclusively showed that such transitions are entirely possible. Further measurements on sealed vials from the original experiment revealed that Miller had created even more amino acids, but without having the capability to detect them. Those new amino acids included variations not used by life on Earth, for whatever reason, our planet having settled on this group of 20 when many more options are available. The Miller-Urey experiment demonstrates one link in the chain of how to create life as we know it. You need to have a prebiotic mixture of elements under the right conditions. And so to find the earliest life could arise, you have to be able to find the right mixture of elements and the right conditions. But where could that be in the universe? Of course, one place we can be sure of is right here, the surface of the Earth, a planet with an abundance of water and a thick, but not too thick, atmosphere. For our Earth sits in what's called the habitable zone of the Sun. This is a region around a star where the temperature is just right. Closer to a star, the intense heat and radiation will boil away any water, turning it into a vapor. Too far away, and that water freezes into solid ice. Every star has its own habitable zone, with the location and size of that zone depending on the nature of the star. Small, dwarf stars have habitable zones brushing right up against their surfaces. Giant stars have habitable zones reaching hundreds of millions of miles away. The habitable zone of the Sun begins just within the orbit of Venus and extends outwards just past the orbit of Mars. But of the three worlds within that zone, only the Earth maintains liquid water in the present day. And so we can conclude from this small example that the conditions for life as we know it are very strict. With Venus, scientists strongly suspect that it once had a thinner atmosphere and supported oceans on its surface. But as the Sun aged, it steadily grew brighter and hotter. Within a few 100 million years, the intense heat from the Sun triggered a runaway greenhouse effect on Venus, evaporating its oceans and building up a thick atmosphere dominated by carbon dioxide. The conditions on the surface are now so hellish that it's hot enough to melt lead. Mars, on the other hand, was also once much warmer, had a much thicker atmosphere, and also had oceans, rivers, lakes, and streams. We see evidence for past water activity everywhere we look on the surface today. But as verdant as Mars once was, it was also born with a fatal defect. It was too small. In less than 1 billion years, it cooled off, its molten core turning solid. Without a molten core, its magnetic field shut off. Without a magnetic field, the solar wind stripped the atmosphere away. The planet dried and died. However, universe-wide, that is relatively small scale. Even entire galaxies have their own habitable zones. Too close to the core of a galaxy, too many stars will live and die, flooding their neighbors with deadly radiation, and the outskirts of a galaxy are too thin with heavier elements, preventing planets from forming in the first place. But to even have the chance for life to appear in the habitable zone of a star or galaxy, with liquid water rich with prebiotic organic compounds appearing on the surface of a planet near a pleasant star, you first need organic compounds and liquid water. Indeed, the origins of Earth's abundant oceans remains a mystery. Certainly, the Earth formed with a lot of water in the first place, as it's the most common element in the entire universe. But most of the water did not end up on the surface. It either got locked up as chemical compounds in the mantle, indeed there's more water in the mantle than anywhere else on Earth, or evaporated while our planet was still molten. Astronomers believe that comets and asteroids likely played an important role in replenishing the water supply of the Earth. These small, leftover bits of debris from the formation of the planets generally formed in the outer regions of the solar system, where water could survive as ice. Then, impact after impact on the young planet brought with it a fresh round of water, which eventually built up to generate our oceans. But again, this process had to be just right. If the Earth suffered too many impacts or too large, then it would have reheated our surface, turning it molten again and sending us back to the start. And it's also possible that these early impacts brought with them something else. In 2014, the Japanese Space Agency launched the Hayabusa 2 mission, a probe headed to the asteroid Ryugu. That mission collected a sample from the surface of Ryugu and returned it to Earth for closer study. Back in the laboratory, scientists were amazed to discover the presence of several amino acids in the dust grains of the asteroid, including some that form the basis of earthly life. And so, it seems that the Miller-Urey experiment is just one of many options available for the universe to make organic compounds and more complex amino acids. Scientists aren't sure how these molecules were created on Ryugu, but it likely involved some complex interaction with the sun's ultraviolet radiation, which could have provided the energy needed to turn simple compounds into amino acids. Considering that Ryugu is a remnant from the formation of the solar system and has remained untouched for over 4 billion years, the timeline would fit for the early arrival of life's building blocks to the Earth's surface. But the presence of amino acids goes back even further than rocks in our solar system. In 2003, a team of astronomers found evidence for glycine, the simplest of the amino acids, in several giant molecular clouds. These clouds are the places in galaxies where stars and solar systems form, so it's also possible that amino acids could have been carried along with the formation of the Earth from the very beginning. Astronomers have also spotted a variety of organic compounds in giant molecular clouds throughout the galaxy, in other galaxies, and even distant quasars. And these quasars only appear in the young universe, suggesting that the basic chemistry for life has been present for a very long time. But even that is not the true beginning. All that chemistry has to come from somewhere. Molecules assemble themselves from elements in a variety of processes throughout the universe, and almost all the elements on the periodic table come from a process known as stellar nucleosynthesis. This process was discovered in 1957 in a landmark paper authored by the husband and wife team of Geoffrey and Margaret Burbidge, along with William Fowler and Fred Hoyle. In their work, they provided a detailed and complete description of how stars fashion elements. The key is nuclear fusion. Our Sun is currently fusing hydrogen into helium to generate heat. Near the end of its life, it will turn to fusing helium, producing carbon and oxygen in the process. When it dies, it will spread these elements out, where they will join the general mix of the interstellar medium. Stars much heavier than the Sun are capable of fusing carbon and oxygen into potassium, magnesium, and more. All the elements, up to and including iron. To generate even heavier elements, the universe has to turn to more energetic processes. Supernovae carry enough energy to fuse many heavy elements, but it turns out that merging neutron stars carry just the right combination of energy, duration, and sheer number of neutrons to produce many more, including gold and silver. And so, to generate life as we know it, we not only need the right conditions, the right chemicals, water, and a temperate planet, but most fundamentally, we need stars. Multiple generations of stars, to be exact, all fusing elements, dying in supernova bursts, and merging together to fill out the periodic table. Only after a galaxy has generated sufficient quantities of the basics, like carbon and oxygen, can water and solid rock form, providing enough material to build planets with the required organic chemistry. But stars have not always been present in the universe. The Big Bang only produced hydrogen, helium, and a scattering of lithium and beryllium, and there were hundreds of millions of years before the first stars ignited. So on our journey to find the earliest possible moment that life could have arisen, we will need to reach back into the darkest ages of the universe. Imagine, years in the future, we finally uncover what dark matter really is. After decades of effort and struggle, it turns out to be quite simple. The vast majority of the mass of our universe is revealed to be made of some new particle that had previously been unknown to physics. Some slight adjustments to the standard model and a series of confirmed direct detections later, the mystery is conclusively solved. a single particle that participates in the gravitational interaction, and very rarely through the weak nuclear force. And that is it. Laboratories are shut down, proposals for new missions scrapped. Without a grand mystery to ignite passion and curiosity, funding dries up, and astronomers and physicists go on to study other cosmic questions. But a small team of scientists persist in their experiments and observations, unconvinced by the accepted explanation. While the new standard model explains the vast majority of dark matter phenomena, there are still some holes. For example, these new dark matter particles can, very rarely, interact with each other, annihilating in a burst of light, a flash of gamma-ray radiation. For decades, we had observed an excessive amount of gamma rays coming from the center of the Milky Way, but long assumed it was due to some particle physics interactions, not dark matter. But this final team working on dark matter thinks there is more. Scraping together funding, they develop a high-resolution gamma-ray telescope aiming squarely at the center of the Milky Way. The gamma-ray signal is there, just as expected, a product of the dark matter particles annihilating. But the more the researchers study the signal, the more questions they have. For the signal isn't perfectly steady, but is constantly changing, ever so slightly. The scientists dream up and discard a dozen theories to explain the variation. Nothing works. After years of study, the funding runs out. The team disbands, frustrated at their lack of progress. But years later, on a sleepless night, one of the former graduate students in the group pulls up the old data. Acting on a hunch, she processes the signal variations in a slightly different way. And then, she sees it. Every few seconds, the gamma-ray signal changes in intensity by a precise amount. Sometimes the signal increases in intensity, and sometimes it drops. The time between shifts, however, never changes, and the up-down pattern never repeats, except after over a month has passed. Then, the same rhythm appears again, and again, and again, marking an increase in intensity as a 1 and a decrease in intensity as a 0. The former student begins scribbling on a nearby piece of scrap paper. 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0. 0, 1, 1, 0, 0. Our quest to find the earliest possible appearance of life in the universe has taken us to the breaking of the cosmic dawn and the birth of the first stars. Those first stars fused only hydrogen and could have been as large as hundreds or thousands of suns. They were born, they lived furious but brief lives, and they died, beginning the cosmic recycling of the elements, each generation of stars to come after, adding to the enrichment of the interstellar medium. Eventually, after an unknown number of generations, a solar system could form, a star orbited by enough rocky and icy material to fashion planets out of the chaos. We know that the first stars didn't appear until at least 100 million years after the Big Bang. We also know, based on observations with the James Webb Space Telescope and more, that galaxies appeared to be fully constructed within 500 million years. There was a time before that, when our universe was 10 to 15 million years old, that the cosmic microwave background flooded the universe with room temperature radiation. But that was well before the development of rocky planets, or even water. And so while we don't yet have a precise answer, we do have limits. The first possibility for life as we know it, swimming in liquid water oceans on a rocky planet orbiting a placid star, would have occurred somewhere between 100 and 500 million years after the Big Bang. Our own solar system formed some 9 billion years later, and so it is safe to assume the Earth was not the first opportunity for our universe to create life. But of course, that's only accounting for the kind of life that we conclusively know of, not the kinds of life that we can imagine. Let's return to our simple definition of life, that which is subject to Darwinian evolution. This requires information storage, self-replication, and the ability to interact with the environment. Life on Earth accomplished this with a soup of chemicals immersed in water, with deep-sea vents or sunlight providing an ample source of energy to drive chemical reactions. And so the earliest life that looks similar to this could not exist for at least a few 100 million years, well after a few generations of stars had already come and gone. But scientists have speculated about many alternative forms of biochemistry. Besides methane, biochemists have also proposed ammonia, hydrogen fluoride, hydrogen sulfide, and silicon dioxide as alternatives to water. Others have proposed that arsenic, which is deadly to almost all life on Earth, might be a useful substitute for phosphorus on some exotic world. Or that silicon, while not as robust and sturdy as carbon, might provide a suitable foundation for complex molecular chains that could lead to intricate living systems. Indeed, in 2007, physicist Vadim N. Sidovich ran computer simulations of molecular interactions and found that dusty grains in interstellar gas clouds, when suspended in an energetic plasma, could begin to self-organize and form complex shapes. Certainly not life itself, but the intriguing hint that something like life could arise. Though whether it's the surface of a planet, deep under a crust or miles of atmosphere, or tucked away in some interstellar gas cloud, all these alternatives ultimately require the same thing: chemistry. The elements of the periodic table have to exist in the first place before they can begin mixing together in interesting ways that can potentially lead to life. And so these alternatives cannot push the emergence of the first life in the universe back much before the kinds we would recognize on Earth. To go further back, we have to get more exotic. In 1973, eminent physicist Frank Drake proposed that microscopic structures inside neutron stars could meet all the conditions for Darwinian evolution. These structures would be bound by the strong nuclear force and could form complex, interacting shapes. Surrounded by the abundant energy of the neutron star's own heat, these structures could potentially begin the path to self-replication. But, of course, to create neutron stars, the universe first has to create stars. And so this possibility pushes back the potential for life to just after the very first generation of stars, some 100 million years after the Big Bang. Another hypothesis, proposed by Louis A. Androdoki and Eugene M. Chodnovsky of the City University of New York, states that life composed of magnetic monopoles connected by cosmic strings could take on complex forms. However, physicists continue to debate the very existence of magnetic monopoles and cosmic strings, and this idea requires that these exotic compounds exist in a heat bath, namely, that they are embedded inside stars. So that still doesn't push the clock back any further. But there is another possibility, hidden in the dark sector of the universe. All of our understanding of physics, from the table of elements to the fundamental particles, comprises less than 5% of all the energy and mass in the entire universe. Most of the cosmos is of a form unknown to modern physics. This unknown is divided into two sectors: dark matter, which makes up the mass of most galaxies, and dark energy, which is responsible for the accelerated expansion of the universe. Despite this categorization scheme, we still don't understand the natures of dark matter and dark energy. They could very well be simple: a particle that interacts with nothing except through gravity, and a quantum force that pervades space-time. Or they could be more complex. New forces of nature could allow dark matter to interact with itself and with dark energy. There could be multiple species of dark matter particles. Entirely new interactions could take place among these particles, allowing them to form their own periodic table of dark elements. Dark atoms, dark molecules, dark chemistry, dark life. a completely alien form of life, using sources of energy beyond our understanding existing in the hidden shadows of the universe. That life could be at play right now, even in the present-day cosmos, completely unobservable to us. And if that kind of dark, shadow life is possible, it could have emerged well before the first stars, as it had access to sources of energy beyond simple nuclear fusion. Perhaps dark life appeared while the universe was still in its plasma state. And that is not the end of it. Simply put, we do not understand the conditions of the extremely early universe. The energies at play when our cosmos was less than a second old are far beyond our current level of understanding. Who knows what exotic forces danced in the fires of the Big Bang? Who knows what structures and patterns emerged? Something like life could very well have arisen in that maelstrom, creating, living, and maybe even thinking. Untold generations passing from one to the next, unknown and unknowable to us in their cold and distant future. A legacy erased by the inevitable expansion and cooling of the cosmos, emerged and extinct in less than the blink of an eye. But even considering all of these remarkable possibilities, if ancient life did arise, how could we ever know? During a pleasant afternoon in the summer of 1950, famed particle physics pioneer Enrico Fermi was walking to lunch with his colleagues. As is usually the case when physicists take a break from work, they started speculating, in this case around the topic of aliens. After debating back and forth for a while on the possibility of extraterrestrial life and the likelihood of encountering it, the conversation eventually moved on. But the question must have dogged Enrico, because later that lunch, apropos of nothing, he suddenly blurted out, "Where is everybody?" The chain of logic is simple. The Earth is not particularly special. Yes, there's liquid water on the surface, a clement environment, a rich soup of organic materials, an abundant and steady supply of energy. We have no evidence of these conditions, let alone life arising anywhere else in the solar system, let alone the galaxy. And yet the universe is vast. There are at least 100 billion stars currently alive in the Milky Way galaxy. There are potentially almost 2 trillion galaxies within the observable volume of the universe. And in physics, nothing happens just once. Either nature forbids it, and it never happens, or it allows it, and the universe is large enough to accommodate multiple instances of even the rarest phenomenon. For example, modern estimates suggest that the Milky Way alone hosts around 5 billion Earth-like planets in the habitable zones of Sun-like stars. And that's just one galaxy. And so Earth is special and life is rare. But Earth isn't that special, and we have no reason to believe life is that rare. We are just one rocky planet orbiting one unremarkable star. If life happened here, then logic dictates it must be a somewhat generic feature of the universe, and so it must have happened elsewhere. And to add to this, the universe isn't just gigantic, it is ancient. Earth-like life could have arisen as early as 100 million years after the Big Bang. The cosmos is now almost 400 times as old. Life appeared on the Earth as soon as the crust cooled and oceans formed almost 4 billion years ago. And so by now, almost 14 billion years after the Big Bang and 9 billion years after the formation of the Milky Way, countless alien life forms should have arisen, crawled out of their oceans, survived terrible catastrophes, evolved to intelligence, developed a sophisticated civilization, and invented the necessary technology to travel among the stars. Even we humans have managed to send a spacecraft beyond the bounds of the solar system and out into interstellar space, and we have been trying for less than a century. Enrico argued that the galaxy should be littered with the debris of alien civilizations, come and gone. There should be active probes in the solar system, remnants of technology everywhere we look. Logically, we should have evolved in the plains of Africa with full awareness of the aliens watching us, even guiding us. And yet, nothing. No sign of intelligence, let alone life, anywhere else in the galaxy. This is Fermi's famous paradox. Life should be everywhere, but instead we are forced to ask, where is everybody? Answering this paradox forces us to tackle the same challenging question again. How would we recognize extraterrestrial life? The most exotic forms of life imaginable, like creatures living in the first instant of the Big Bang or within the dark sector of the universe, would likely remain elusive to us forever, with any evidence of their existence hidden from even our most clever experiments. But Earth-like life, or even life based on exotic chemical combinations, that is a different story. One answer is to focus solely on intelligent life, as the thinking goes that while intelligent civilizations may tend to be rarer than generic, simple life, they are at least loud. As soon as humans developed radio technology, for example, we started blasting signals around the world and out into space. This is the backbone of SETI, the search for extraterrestrial intelligence. The general SETI program searches for radio signals produced by artificial means. Radio is especially handy because it's easy to generate in large quantities with relatively little power, and it can sail through thousands of light years of interstellar dust clouds without getting itself scattered or absorbed. Unfortunately, after decades of scanning the radio skies for any signs of intelligence, we have found nothing. One possibility, of course, is that we have only barely scratched the possible search space. After all, astronomical observations are difficult and expensive, especially when they are across a broad range of frequencies, across the entire sky, and as often as possible. So, we may have simply missed the few stray artificial radio signals that have washed over the Earth in the past half-century. But other SETI attempts have also failed. Alternative directions have focused on searching for physical artifacts of intelligent civilizations, like alterations of stellar chemistry as a signal to the wider universe, or the construction of mega-engineering projects like Dyson spheres. But no known stars show signs of artificial pollution, and no Dyson spheres appear in our scans across the galaxy and out into the wider universe. Besides these searches for intelligence, hunts for any forms of life have also come up empty, despite our trying every possible angle. We've searched for alien worlds orbiting within the habitable zones of their stars. We've studied the light filtering through their atmospheres, looking for biosignatures like excess oxygen and methane, something that could not possibly have a purely chemical origin, no matter how exotic. And while many of these searches are still nascent, the ones we have performed have still come up empty. We've found thousands of exoplanets and many potentially habitable worlds, like the TRAPPIST-1 system or Proxima b, and many with thick atmospheres. And yet in all that work, we haven't found a single shred of evidence for life outside the Earth. And so, where is everybody? The first possibility to consider is that Fermi's base assumption is wrong, that life truly is rare. The Earth and our conditions being special, if not entirely unique within the galaxy, that you could have 1,000, 1,000,000, 1,000,000,000 copies of Earth, all with the exact same temperatures and pressures and soup of chemicals, and life would only appear on one of them. Or perhaps, while life may be common, intelligent life is not. Perhaps there are microbes on almost every wet world in the galaxy, but that in 14 billion years of cosmic history, we are the first intelligent civilization to arise in the Milky Way. To beat the astronomical odds stacked against us and look into the universe with curious minds. That we, for all intents and purposes, save for some microscopic cousins that we might encounter in our explorations in the distant future, are alone. Life could have been right in front of our eyes from the start, but of a chemical form that we cannot yet distinguish from non-life. Perhaps creatures really did once crawl through that Martian meteorite. Perhaps the buried seas of the outer moons are alive and active, but we may not yet realize it for what it is. And of course, yet another possibility is that both life and intelligence are common, but not for long. Life may gain foothold after foothold on countless worlds, only to be snuffed out. Just looking at our own geologic history illustrates the risks that being alive brings. How many times was the Earth almost wiped clean, and that even before the rise of sentience? Once intelligence arose, we developed the capability to destroy ourselves relatively quickly, but perhaps still lack the sophistication to assure our own survival. Proliferation of nuclear weapons and the spiraling disaster of climate change may not threaten us as a species, but it could certainly spell doom for our ability to communicate with the wider cosmos. Could we possibly recover our technological might from such a catastrophe? Or would we linger on for generations, returning to the ways of our ancient ancestors until some larger calamity consumes us? But let us put that to one side and imagine we prevail. Perhaps we do spread throughout the solar system and even the local galaxy, overcoming the vast distances that separate the stars. Perhaps we endure for 1 million years or more, an unimaginable amount of time to remain technologically sophisticated. The problem is, that is almost nothing on a cosmic scale. The universe is 13.8 billion years old, our home galaxy, one of trillions. Eventually, some limit is reached, and we simply dwindle away, with nothing more than empty worlds and dead space probes